because question number 1 asks a question in a way that I was taken off guard when I had to go answer it. And I think it makes for a good conversation. My plan today was to do a live quiz and then to talk to you about your homework a bit. Since there isn't a live quiz today, we're just going to talk a little bit about the homework. But having none of you give it a real shot makes it hard for us to talk about it, right? Right. So here's the first part of the homework, and I'm going to ask only one question about it, because it's the second part of the homework that I find to be interesting. There's an arrow that's going to be fired into a block, but the block is like locked into the ground so that it can't move. The arrow is then fired in such a way that it embeds the block a distance d, is what they say in the problem. And there's lots of different symbols used in the problem, so I kind of got to get these right, or else it doesn't seem to work. And let me color the arrow something that will provide some contrast. So here's the arrow launched at Vx, mass m, and it embeds itself into the block a distance d. And it says that while it's entering the block, it experiences a frictional force. It's not friction. It experiences a force from the block, capital F something or other. Now there's several questions related to this in part A, B, C, and D of the problem. And I don't want to go through all of those because you need to. Those were not the hard parts. The hard part begins, I think, in question E, which is perhaps why it was hard for me, because I didn't do the first parts this way. I was just asked about question E without having done the other parts ahead of time. In question E, having difficulty here. I don't want that. I don't want that at all. I'll just do it this way. In question E, the block is no longer attached to the surface. So the block is free to slide on the surface after it's been hit by the arrow. So the arrow embeds the block, and then the block and the arrow slide across the surface. So I'm kind of imagining that there are 3 stages to this question. And also at the same time, I know that your screens, for those of you who are looking at this on phones, might be hard to see. So I'm trying to make things kind of big, but it means it's going to take up more room. So I kind of envision that there are 3 parts to this question. There's the instant before the arrow is embedded in the brick. There's the instant after the arrow is embedded in the brick now. But now, keep saying brick, but I mean block. But now the system also is not attached. So this is going to imbue the system with some momentum. And the system is going to be sliding to the right and will eventually come to rest with the arrow stuck in the block, having slid some distance, capital D. And the suggestion in the problem is that when the arrow strikes the block under these circumstances, it goes into the block a different distance, even though it was launched with the same velocity and all that. Now, in this problem, they give us all sorts of variables. Lowercase m for the mass of the arrow, capital M for the mass of the block. We're told that the arrow is fired with the same initial velocity, Vx, as it was in part A, B, C, and D. But they then ask for dn, which I didn't think would be a big deal. I'd start talking about momentum. It seemed like a collision question to me. But herein lies the rub. We're not allowed to put any of the masses or any of the velocities in our expression for dn, which means that kind of takes away any chance of using momentum, since momentum is going to be all about inertia. So when I was working this problem with Savri and Wes and even Anna Kate to some extent, my initial thoughts were to start looking at the momentum, and probably maybe the mass would cancel out somewhere, but the mass of the block and the mass of the arrow are different, and there's no place for it to cancel out. So I was really thrown for a loop as to what I was supposed to do, since I couldn't have the masses in there. And I started looking at what I was allowed to have in my answer. And it let me have how far the block slid. It let me have the frictional force on the block as it slid. It let me have the force on the arrow as it penetrated the block. And it let me have the original distance that the arrow was embedded into the block. And that was it. So when I first looked at this problem, I was like, maybe the stuff will cancel out. Maybe we can use kinematics, like we'll get the velocity here after the collision, and we'll use kinematics to figure out how far it goes, and maybe from that we'd be able to cancel out the V's. And so I went on this long, I've got 4 or 5 pages of Blackboard stuff, but it all ended up having combinations of the masses in there someplace and the initial velocity, all sorts of stuff. So that's when I went back and reread the problem. But there's issues with the problem, and there's issues with the way I attacked the problem. This problem isn't about momentum. They want this problem to be about energy, and that's what they've made this problem about. This is an energy problem, not a momentum problem, which is a little bit unusual, because I would have come at this problem from the standpoint clearly of momentum, because it's a collision. Now, to understand this problem, and this is why I want to go over it with you guys in class, we do need to go back to the prior problem, because having looked over AP's work, what they really want us to consider here is the Work-Energy Theorem. Which them giving us the forces should have been something I would have considered from the beginning. But I just didn't. Because they give us all the forces, which means we can figure out work. In this problem, the arrow starts with kinetic energy. And it's going to come to rest, which means we know the change in kinetic energy, because we know it's going to come to rest. More importantly, in the initial part of the problem, we know that the kinetic energy will have to be, the change in kinetic energy will have to be equal to the work done on the arrow. The arrow's final kinetic energy is 0, and its initial kinetic energy, I'm just going to write as K. We know that that's 1/2 mvx squared, but it doesn't matter. We can't use any of those in our answer. On the other hand, there are 2 variables we can use to figure out the work done on the arrow, because work done is force times distance times the cosine of the angle between them, which for the force on the arrow is F d and the cosine of 180 degrees, making this negative FD. which in the first part of the problem tells us that the kinetic energy of the arrow is equal to Fd. This is important. It's important for a huge reason. They tell us that they launch the arrow at the same speed in the second part of the problem, which means in the second part of the problem, the kinetic energy of the arrow is also equal to Fd. That's why these two were variables that were allowed in our answer. Keep going. All right, well, let's talk about the next part of the question, because the next part of the question is a little, like I said, it's tough. And I actually have a problem with something AP did on this question, so I'm going to have to bring that up too. In the next part of the problem, they ask us, again, to figure out dn. They want how far the arrow goes into the block. And I'm only allowed to use these variables that are presented here. And I do know that the block and the arrows slide. They want us to use the work-energy theorem again. And they want us to do so because, well, and this is a bit of a stretch, but I want you to walk this one with me a little bit. I'm going to not really have a lot of space here, so I'm going to erase this so I have a little space. They say, using the work-energy theorem, that the arrow has kinetic energy at the start of this problem. And its kinetic energy is going to be brought to 0. So there's going to be a change in kinetic energy of the arrow. Now, if we consider conservation of energy for a minute, this is the amount of energy that's brought into the system. Does that make sense? This will have to equal the work done on the arrow by the block. That's going to take some of the energy out of the system, right? The arrow is going to slow down. Does that make sense? And then, just to make a little more room here, I'm going to have to reduce where this D is. And then, and this part's a little tough to stomach, they go on to say that we're also going to have to consider the work done by friction on the block. Now, this is in their solution manual. What's interesting, though, is that they don't talk about something I would subtract here, which would be the work done on the block by the arrow. I mean, doesn't the block speed up because the arrow hit it? Wouldn't that be true? And if you're asking why I'm subtracting it, I'm saying, well, that's taking arrow energy away from the arrow and putting it in the block. So the block would now have kinetic energy because it's moving. The reason I would not have thought to do this is because they want us to ignore this, which doesn't make any sense to me, because you don't have to ignore it if you use momentum. And I've been reading the problem over and over again to figure out how would I know to ignore that. And if you have the problem up, and many of you probably don't, but if you have the problem up, I'll tell you how they slipped in one word. They say that the arrow struck the block and was embedded instantaneously. That's the special word. And I see Sarah nodding there. Yeah, basically that they say that this collision happened so fast that the block didn't have a chance to move while the arrow was being embedded in it. Now, the problem with that is, and this is a big problem for me, the block didn't have a chance to move, but the arrow did. Doesn't make a lot of sense. That's not how physics works. The block would have moved to the right while being sped up. But they want us to ignore that And that's how the problem is done. Because the kinetic energy of the arrow initially, we already know, is FD. The work done by the block is the same force still, but now it's how far the block went in on these new circumstances, plus the work done by friction bringing the block to a stop. The reason the masses aren't here is because things like the force of friction would have probably the mass embedded in it, because it'd be based on the normal force and stuff like that. And since they gave us the frictional force, that's where the mass of that kind of stuff is located. Now, this is actually the answer. They want you to solve this for dn, and that gives you the basically how far the arrow would embed itself in the block based on the forces of friction and the original distance the arrow is embedded in the block. Not a big fan of this question now that I've had to do it. I probably won't assign it next year. But part F is back to our normal kind of conservation of momentum stuff. You're allowed to bring the masses back into your answer. It makes more sense to me. This one just did not. I'm unhappy with this question. But I didn't want you to get stuck on number one. A through D aren't terribly bad. E, though, it's pretty... I'm not sure how you were supposed to figure out to do this. I'm not sure. I mean, maybe you might have figured it out. I would not have thought to do this. So that's problem number one. So I'm gonna